A quadratic irrational can be represented by a periodic infinite simple continuous fraction. How we can prove it? Let y be a quadratic irrational. Then we can write y0 equal to y and a0 equal to greatest integer of y0, and y1 equals to 1 by y0 minus a0, and a1 equals to y1 greatest integer, and dot dot, and yn equals to 1 by yn minus 1 minus a n minus 1 semicolon, an equals to yn greatest integer. Here all the yns, as you can see, these are quadratic irrational. Then let y equals to a0 semicolon a1 a2 dot dot an comma yn. We have to show that for some value of n, yn is reduced quadratic irrational. So that we have to prove yn is greater than 1, and second one is minus 1 less than equals to yn conjugate less than 0 for some n. These two properties we have to prove. So then we can say this is reduced quadratic irrational. Yn greater than 1 for all n greater than 1. y1 equals to 1 by y0 minus a0, a0 equals to y0 greatest integer of y0, y1 equals to y1 is greater than 1. Since 1 is greater than yn minus a0 greater than a0, now y equals to a0 semicolon a1 a2 dot dot an minus 1 comma yn for any n greater than equals to 0. We know that cn equals to, that is hanging problem, pn divided by qn equals to an p n minus 1 plus p n minus 2 divided by an q n minus 1 plus q n minus 2. So this type we written yn equals to yn p n minus 1 plus p n minus 2 divided by yn q n minus 1 plus q n minus 2. We just take the conjugate of yn. We take conjugate. We just multiply this to this, then yn conjugate, yn qn minus 1 plus yn bar qn minus 2 equals to yn bar pn minus 1 plus pn minus 2 equals to y bar yn bar qn minus 1 minus yn bar pn minus 1 equals to minus yn bar qn minus 2 plus pn minus 2. We just common yn bar terms, so this become this. We just put here, then we just common minus qn minus 2 from this term. This positive sign become here negative sign. That's it. And we know pn minus, we know pn equals to so this term becomes cn minus 2 and this term becomes cn minus 3. As n tends to infinity, this term becomes 1 equals to yn bar equals to minus qn minus 2 divided by qn minus 1 equals to or imply, then this term become this side goes to this 1 equals to minus qn minus 2 divided by qn minus 1 yn bar minus qn minus 2 divided by qn minus 1 yn bar minus 1 equals to 0. So this term goes to 0. Now for epsilon greater than 1 there exists an integer n0 such that we can write mod of minus qn minus 1 divided by qn minus 2 conjugate of yn minus 1 is less than 1 for all n greater than equals to n0. That is minus 1 is less than minus qn minus 1 divided by qn minus 2 yn mod minus 1 less than 1. We just addition of we just add plus 1 each term, then this becomes 0 and this term become this and this term become 2. We know this is negative, then the yn bar also it should be negative. Implies that yn bar is less than 0, all n greater than equal to 0. By definition we know the conjugate of yn bar plus 1 equals to 1 by yn bar minus an, all n greater than equals to 0. since yn conjugate is less than 0 for all n greater than n 0, and an greater than equals to 1, all n greater than equals to 1, for all n greater than equals to n 0, we can write yn conjugate minus an less than minus 1, then it's 1 by yn minus an is greater than minus 1 for yn. This term is from this we can write yn n plus 1 conjugate is greater than minus 1 for all n greater than equal to n 0, imply yn is greater than 1 for all n greater than 1. That is imply that minus 1 is less than equals to yn plus 1 bar which is less than equal to 0 for all n greater than equals to n0. In particular, if n equals to n0 plus 1, then minus 1 less than equal to yn bar less than equal to 0, imply y equals to a0 semicolon a1 a2 an0 comma a comma y n0 plus 1. Since y n0 is reduced quadratic irrational, then it has a purely periodic infinite simple continuous fraction. Let y n0 plus 1 equals to b0 b1 b2 bn repetitive bar. Y equals to a0 semicolon a1 a2 an0 comma b0 b1 b2 bn repetitive bar, then which is a periodic infinite simple continuous fraction. Prove